Hi, Mr. Green here. I'm going to take you through the next topic in the Physics AQA GCSE, and this will be on atmospheric pressure. Our learning objective today is to know how and why atmospheric pressure varies. Please pause the video whilst you write that down as your title. Okay, so we've got some retrieval questions to start with. If you just pause the video whilst you attempt these 5 and then restart when you like the answers. Okay, question 1. What's meant by a fluid? A fluid is a liquid or a gas. Anywhere where the particles can move around or flow would refer to as a fluid. Question 2. What's the equation for pressure? Pressure is force divided by area. So the force that's applied divided by the area over which that force acts. What's the unit for pressure? Pressure we would say is in pascals. You could say it's newtons per metre squared, but we'd also refer to it as pascals. What's the equation for pressure due to a column of liquid? The pressure due to a column of liquid is equal to the height of the column multiplied by the density of the fluid multiplied by the gravitational field strength. So it's how tightly packed that fluid is together, how much the Earth's pulling it down, and how high the column is that will all influence the pressure. And question 5. When will an object float? The object will float when the weight of the object is equal to the upthrust that's provided to the object. Okay, so today we're going to be looking at how the atmosphere changes with height and looking at how we can describe that, and describe and explain how atmospheric pressure changes with height. Okay, so what is the atmosphere? So the atmosphere we describe as the layer of air that's all around the Earth. Now, compared to the size of the Earth itself, the layer of the atmosphere is extremely thin. It's made up of 4 different bits. It's made up of the troposphere, which is right close to the Earth, the stratosphere just above that, the mesosphere, and the thermosphere. We add all those together, we get our atmosphere. How does the atmosphere change then? So as we travel higher up through the atmosphere, the density of the atmosphere decreases. So look at that diagram I've just shown. Which would be the least dense? Which would be the most dense? Okay, the most dense in this case would be the troposphere. That's the lowest down, it has got the lowest height from sea level. Whereas the lowest density, the one where the particles are furthest apart, would be the thermosphere, because that's as far away as it can get. As we increase height, we decrease density. Just as a quick recap, how do our gases exert pressure? There is a lesson on gas pressure itself, so you can go back to the YouTube channel and look for the gas pressure video. But if we're already confident on that, how do gases exert pressure? Well, if we look at that diagram there, we can see the particles in the gas within a container. Pressure is equal to force divided by area. When placed in the container, the particles of a gas which are able to move and move around will collide with the walls of the container. This exerts a force across the area of the particle. So every time a particle hits the walls of the container, pressure is exerted. The sum of the individual pressures of each individual particle, we add those together, and that gives us the total pressure of the gas within that container. Okay, 5 quick questions for you there. Please pause the video and attempt them to see how you've progressed. Okay, question 1. What's meant by the atmosphere of the Earth? That's the thin layer of gas that's all around the Earth. What happens to the density of the atmosphere as we travel further away from the Earth? As the height increases, the density of the atmosphere decreases. What causes gas pressure? That's gas particles colliding with the wall of the container. Question 4. If we increase the temperature of the gas in the container, what would happen to the pressure and why? If we increase the temperature, the pressure would increase. The particles have more energy and therefore they would move more, colliding with the sides of the container more often and with more force. This overall would increase the pressure. And question 5. If we increase the volume of the container but kept the amount of gas constant, what would happen to the pressure and why? The pressure would decrease. As the container is a lot larger, the particles wouldn't hit the sides of the container as often as if the container was small. So this would decrease the pressure. There'd be fewer collisions with the sides of the container meaning pressure would decrease overall. So what's atmospheric pressure? We know what gas pressure is, we know the atmosphere is made of a gas, so therefore it must exert a pressure. Air molecules that collide with surfaces cause atmospheric pressure, and atmospheric pressure is caused by the force exerted on the surface by the air above it as gravity pulls it towards the Earth. Now atmospheric pressure at sea level is around 101,000 pascals, or we'd refer to that as 101 kilopascals. Pascals is the standard unit for pressure, but another unit we use sometimes is the bar. 1 bar equals 100,000 pascals, so atmospheric pressure we sometimes refer to as 1 bar of pressure. You can see the bottle in the diagram there. The arrows represent the atmospheric pressure that's experienced by that bottle. All the gas particles around the outside are bouncing off the sides of the container. So the atmospheric pressure is provided outside that. How does a barometer work then? Barometers can measure changes in atmospheric pressure, and they can be used in some cases to predict weather. They can be used to predict when changes in pressure will occur. Now most traditional barometers use mercury. The mercury is in a really long glass tube with an open reservoir at the bottom, like this. So we have a big tube, we fill that with mercury, there's a vacuum at the top of the tube, and the atmospheric pressure pushes down on the mercury. When there's a higher atmospheric pressure, it exerts a much bigger downward force on the mercury in the reservoir. This then pushes the mercury up the tube. So we could see from the scale that the mercury would be a lot further up that tube. That indicates a high atmospheric pressure. When the atmospheric pressure is lower, it can't hold up the weight of that column as effectively. So it doesn't push down on the reservoir as much, which means the level in that tube decreases somewhat, and so we can see that it's a lower pressure. Now we can show atmospheric pressures acting on cans using this experiment. Take about 1 centimetre depth of water and place it into a can, so in a can of water or a can of Coke. Hold the can over a gas flame until the water starts to boil. We'll feel the boiling and we'll see wisps of steam coming out of the top of the can. We'll let the water boil for a minute or so. Remove the can from the flame and we immediately turn it upside down and dip the open end into the bowl of water. A fraction of a second later there will be a bit of a bang and the can will collapse. That's how it should look. Going to have a brief look at the video now. You can find the video linked there. Okay, we can see this happening in slow motion here. That can has had the water heated out of it and it's going to be placed within that reservoir of water. So we've done those first few steps. This is in slow motion. As the water hits that, see what happens to the can. We see suddenly it collapses in on itself. We need to explain why that happens. Okay, so why does this happen? Well, initially the air pressure inside the can is equal to the air pressure outside of it. So inside and outside the can it's equal. The thin metal of the can's got equal forces pressing on it from either side, so there's no overall force. So inside the can and outside the can is equal pressure. When we boil the water in the can, the water evaporates to form steam. So as it does so, it gets a lot larger. A really small amount of water in the bottom of the can could fill it many times over with steam. As more water boils, more and more steam is produced, and that pushes the air that's inside the can out of the can until the can's completely full of steam. The steam exerts the same pressure inside the can as the air does outside, so it's replaced the air in there, so the can remains unharmed. However, when we dip the can into the bowl of water, the steam cools really quickly and rapidly condenses into liquid water. Because it's a liquid, it's not exerting that gas pressure anymore, so the pressure inside the can has suddenly dropped. So we can see what's happening there. Outside, we've got lots and lots of air pressure on the outside, but on the inside, the pressure's suddenly really low. When the steam's all condensed, the inside of the can is nearly a vacuum, and so now there's no pressure inside the can to resist the air pressure outside it. The air instantly crushes the can. That can is being crushed by atmospheric pressure. We can also show this with things called Magdeburg spheres. 2 Magdeburg spheres are shown there. If we place the hemispheres together, they're dead easy to separate, and this is because the air pressure inside the hemisphere pushing out and the air pressure outside pushing in is equal. There's no overall pressure. However, if we place them together and remove the air from inside the spheres, we can't separate them anymore. That's because the air pushing outside the hemisphere, pushing in, is much higher than the pressure pushing out inside the hemispheres, which is almost zero because we've removed the air from inside the hemispheres. Holding them together is the atmospheric pressure. There's pressure pushing those 2 hemispheres together, making it a sphere. So why does atmospheric pressure change with height? When the altitude increases, the density of the atmosphere decreases. That means the number of air molecules decreases, so the weight of the air decreases. And as we move further away from the Earth, there's less air pushing down on us. Again, that decreases the atmospheric pressure. We can see from that diagram at the top, that first diagram, when we're closer to the Earth, the molecules, all those molecules above us, contribute to the pressure at that altitude. But as we move further up, it's only the air particles above us that contribute to the pressure. Those below don't do that. As it's less dense further up, that means there's less pressure on us the further up we go. Now, aircraft normally travel at around 30,000 to 40,000 foot. 4 questions on there. Pause the video and attempt those questions for me. Okay, question. What will the atmospheric pressure be like at this altitude? At such a high altitude, the atmospheric pressure will be really low. The actual value is 23.9 kilopascals compared to 101 at sea level. What issues could that cause the passengers? The air is really thin, and your lungs are used to breathing air at around 101 kilopascals. So it's really difficult to breathe at that pressure, yet lungs wouldn't be able to take in as much gas as quickly as they could. Now, if that's dangerous, why do planes travel at that height? They travel at that height because the low atmospheric pressure means there's less air resistance, so we need less fuel to get up to a high speed. So how can we get around this? How can we make it safe for passengers to fly at this altitude? We pressurise the cabin. We put artificial pressure in the cabin so it feels the same as being on the ground. So we pump air into that cabin so that the pressure is the same as being on the ground. Passengers are able to breathe easily and they don't feel the effects of that low atmospheric pressure. Okay, next thing. Look at those crisp packets that have been taken up to the top of a mountain. Why does this happen to them? Pause the video whilst you tell me why. Okay, the reason this happens to crisp packets taken up a mountain is at sea level the atmospheric pressure is normal and the crisp packets appear normal. As we go up the mountain, the atmospheric pressure decreases, but the gas pressure in the seal crisp bag remains the same. At high altitudes, the air pressure in the crisp bag is much higher than the atmosphere surrounding it, so it doesn't push down on the packet as much. So as a result, the crisp packets swell, and as the pressure inside the bag is greater than that outside the bag. If you carried on going up there, eventually those crisp packets would pop, the pressure would be so much. Okay, how does atmospheric pressure help us drink through straws? You can see from the video, from the picture there, atmospheric pressure is pushing down on the surface of that. So there's a uniform amount of pressure pushing down on the surface of the liquid. When we suck on the straw, we remove air particles from the straw. This makes the pressure in the straw much lower than the pressure on the liquid outside the straw. This difference in pressures forces the liquid up the straw to equalise the difference in pressures. Okay, I've got some questions for you to do here. If you could pause the video and answer those first 3, restart when you'd like the answers. Okay, 1. What causes atmospheric pressure? It's caused by the force exerted on the surface by the air above it as gravity pulls it to Earth. What is the value of atmospheric pressure at sea level? Give 2 values, 101,000 pascals or 1 bar. How does removing the air between 2 Magdeburg hemispheres cause them to stay together? When we remove the air, this causes a difference in pressures inside and outside the hemispheres. The pressure outside is much higher than the pressure inside, and this forces those hemispheres together. 3 more questions to do. Pause the video whilst you attempt those. Okay, so why does atmospheric pressure decrease with altitude? It's because as we move further away from the Earth, there's less air pushing down on us, decreasing the atmospheric pressure. Why are the cabins of aeroplanes pressurised? It's because the cabin is pressurised so it feels the same as being on the ground. Passengers are able to breathe easily and don't feel the effects of that low atmospheric pressure. And question 6, how would placing a lid on a soft drink affect how easy it is to suck the drink up through a straw? If we were to place a lid on the drink, we reduce the amount of atmospheric pressure pushing down on the surface. This means sucking on the straw in a normal way wouldn't produce the same difference in pressures than without the lid. We would have to suck a lot harder to get the same difference in pressure. Okay, hope that was useful for you. Please check our YouTube channel for more videos explaining the concepts in physics. Thanks a lot. Goodbye.